The equations that allow us to calculate the Doppler effect have several variables, and it's important to know what the variables and their subscripts mean. First off, the source of the sound could be moving, and v sub s is the velocity of the source. It's also possible to get the Doppler effect by having the observer move, and v sub o is the velocity of the observer. Ordinary v with no subscript is the speed of sound. F sub s is the frequency that is emitted by the source, and F sub 0 is the frequency heard by the observer, or the frequency that is received. Now, the simplest possible case is that both the source and the observer are not moving. And in that case, if there's no source or observer motion, the frequency that is emitted by the source is the same frequency that is heard by the observer. On the other hand, if you have either a moving observer or a moving source, then there will be a shift in the frequency that is received by the observer. So if the source and the observer move towards each other, there will be additional wavefronts encountered per second. So you can see in the cartoon animation below that you have a source that's emitting 800 hertz. As it approaches an observer, the observer receives a sound that is higher, 820 hertz, because they are encountering additional wavefronts per second. As the source moves away from the observer, however, there are fewer wavefronts encountered per second, and the frequency of the sound that is observed drops to 780 hertz. So this shows what happens with a moving source. The observer could also be moving, and in this cartoon picture over here, you can see that if an observer is running towards the source of the sound, they would be running into additional wavefronts per second. You can think of this like a boat that is moving through water that has waves in it. If the boat goes into the waves, they will be encountering more wave fronts, more wave peaks per second than if they were just stationary. And so the pitch or the frequency of encounters is going to be higher. The opposite is also true. If the observer moves away from the source of the sound, then it will take a little while for each wavefront to catch up to the observer, and so the frequency that is observed will be lower. So here's the expression that is used to calculate this shift in the frequency that is observed. So on this side, on the left-hand side, this is the frequency that is observed by the listener. Here's the frequency emitted by the source. Ordinary v is the speed of sound. This is the speed of the observer. This is the velocity of the source. So when we're using this equation, it's important to keep in mind the appropriate sign conventions so that we get the right Doppler effect shift. So if the observer is moving towards the source, if the observer moves towards V naught, V sub O is positive. If the observer moves away from the source, then velocity of the observer is negative, meaning you plug a negative number in for V sub O. If, on the other hand, we are looking at the source and the source is moving, then if the source moves towards the observer, then V sub S is positive, and if the source moves away from the observer, V sub S is negative. So you should be plugging a negative number in for V sub S. And it could be true that both the observer and the source are moving, in which case you would have to see whether the observer is moving towards the source or away, and whether the source is moving towards the observer or away. So next, let's look at an example problem where we can calculate this Doppler shift. So in this example, we have a 500 hertz whistle moving towards a listener at a speed of 10 meters per second. At the same time, the listener moves at a speed of 20 meters per second in a direction away from the whistle. So what would be the apparent frequency heard by this listener? All right, so let's write down some of the facts that are given to us in this problem. We know that the source is producing a sound at 500 hertz. So the frequency of the source is equal to 500 hertz. And what we're trying to calculate is the frequency that is observed by the listener. So the frequency that's observed. We also know that the velocity of the source is equal to 10 meters per second. And we're told additionally that the whistle is moving towards the listener. So the source is moving towards the observer, and so this velocity of the source is positive because the source is moving towards. At the same time, the observer is moving at a rate of 20 meters per second, and the observer is moving away from the whistle. So since the observer is moving away from the source, that would be a negative 20 meters per second. Towards is positive and away is negative. So if we were to draw a picture of this scenario, we have our whistle, and the whistle is traveling at 10 meters per second, and this is the source, and our listener they are moving away from the source with a speed of 20 meters per second. Okay, so we know that the expression for the Doppler shift is that the frequency heard by the observer is equal to the frequency of the source times the speed of sound plus the velocity of the observer divided by the speed of sound minus the velocity of the source. And we're told that the speed of sound, we should take that as 340 meters per second. So we can plug in numbers. The frequency produced by the source is 500 hertz. The speed of sound, we're told, is 340 meters per second plus the velocity of the observer, and the velocity of the observer is a negative 20 meters per second divided by the speed of sound, 340 meters per second, minus the velocity of the source, and the velocity of the source is a positive 10 meters per second. So then the frequency that is heard by the observer is going to be equal to 485 hertz. So the observer will hear a lower pitch for the whistle than is being emitted by the whistle in its own rest frame, because overall the observer is moving away from the source. The 20 meters per second is bigger than the 10 meters per second. So here's another question for you. Let's say you're driving down the highway in your car when a police car sounding its siren overtakes you and passes you. If its frequency at rest is F0, how is the frequency you hear different from F0 while the police car is catching up to you?